Good evening, everybody. Today we will discuss the kinetics of composite reaction or complex reaction. In the last class, we have discussed the integrated rate expression for the first order, second order, third order, nth order, and zero order reaction. But the many of the chemical reaction are not simple reaction, just like our first order, second order, etc. So there are some of the chemical reaction which consisting of combination of two or more reactions. So that type of the reaction is known as composite reaction or complex reaction. So composite reaction or complex reaction is a reaction in which the rate expression involves the rate constant of more than single elementary reaction. That means one or more steps are involved in the chemical reaction and the rate of a reaction depend upon more than one step. So these are the some of the different type of the composite reactions. First one is opposing reaction, second one is the parallel reaction, and the third one is the consecutive reaction. Let us discuss each type in detail. Now we will discuss the opposing reaction. Opposing reaction is otherwise known as reversible reaction. So any reaction in which the forward and backward reaction occurs simultaneously to a noticeable extent is known as opposing reaction. In the opposable or reversible reaction, the product also simultaneously react and to give back the reactant. So such type of the reactions occur in equilibrium state when the two opposing reaction are in equal quantity. Okay, this is the definition of a opposing reaction or reversible reaction. And based upon the order of the forward and backward reaction, we can again classify the reversible and opposing reaction into three different type of category. So first one is the both the forward and the backward reaction is of first order reaction. See the example, A reversibly gives B. Here A is the reactant of the forward reaction and B is the product of the forward reaction, and simultaneously B is the reactant of the backward reaction. So next example is the first forward reaction is first order and the backward reaction is of second order. See this example, A reversibly gives B plus C. Here the forward reaction there is only one reactant A, whereas in the backward reaction there are two reactant B and C. So next type is both the forward and backward reaction are of second order. So in the forward reaction A and B react together, whereas in the backward reaction C and D is react together. So these are the three different type of opposing reaction. First one is the forward and backward reaction are of first order reaction. Second one is forward reaction is first order and second backward reaction is second order, or it may be forward reaction may be second order and backward reaction may be first order. Then the third type is both the forward and backward reaction is of second order. Let us discuss the each type in detail. First of all, we are moving into the integrated rate expression for the first order reaction, which is opposed by the first order reaction. See the general reaction, A reversibly gives capital B, and here the rate constant for the forward reaction is Kf and the rate constant for the backward reaction is Kb. And let the concentration of the capital A is small a. After a time interval t, the concentration of A is reduced to A minus x and the product B formed is the x. So now if we write the rate expression dx by dt, that's equal to See here, first of all, we have to write down the rate expression for the forward reaction, that is dx by dt is equal to Kf into concentration of the A. Here it is A minus X. Then we should also combine the rate constant for the backward reaction, because the forward and backward reaction occurs simultaneously. So in order to represent the backward reaction, we have to represent minus the rate constant for the backward reaction Kb into concentration of the X. Okay, so our final rate expression for the opposing reaction is dx by dt is equal to Kf into A minus X minus Kb into X. Now at equilibrium, what will happen? At equilibrium, the rate of the forward reaction and the rate of the backward reaction must be equal. That means X become Xc. That is the variation in the mass at equilibrium state. So X become Xc. So above equation 1 become dx by dt, that's equal to Kf into A minus Xc minus Kb into Xc. And since at equilibrium the rate of change of the concentration, that is dx by dt, is equal to 0, because both the reaction are occur simultaneously and there is no visible change of the change in concentration will occur. So that's why dx by dt is equal to 0. So our equation becomes 0. So Kf into A minus Xc minus Kb into Xc, that's equal to 0. Then if we move the Kb term to the right hand side, what will happen? Kf into A minus Xc, that's equal to Kb into Xc. So Kb is equal to Kf into A minus Xc divided by Xc. So we find out the constant Kb in terms of Kf into Xc. Then let us substitute the value of the Kb in the first equation. Then after rearranging, we will get the rate constant for the integrated rate constant for the first order reaction, which is opposed by the first order reaction itself, is K is equal to Xc by At into ln Xc by Xc minus X, where Xc is the change in concentration at equilibrium and X is the change in concentration and At is the time. So this is the integrated rate expression for the opposing reaction, in which both the forward and backward reaction is the first order. Now let us discuss the first example for this type of the opposing reaction. Ammonium thiocyanate converted into urea, in which we can see that both the forward and backward reaction are first order, and the rate constant for the forward reaction is Kf and rate constant for the backward reaction is Kb. Now we are moving into the next type, that is forward reaction is opposed by the second order reaction. See, in the general example, we can see A reversibly gives B plus C. And here the forward reaction is first order and the backward reaction is second order. Then initially the concentration of A is A, small a. After a particular time interval, the concentration reduced to A minus X, and similarly the concentration of B is X and concentration of C is again X, because after a time t interval B and C is formed in the reaction medium. So our net rate expression is dx by dt, that's equal to Kf into concentration of A minus X minus Kb into concentration of the X whole square power. So always keep in mind, if the reaction is an opposing reaction, then we should write the forward reaction, then followed by minus the rate constant for the backward reaction into the concentration of the reactant which is present in the backward reaction. So equation become, rate expression become dx by dt is equal to Kf into A minus X minus Kb into X square. So one of the example is gas phase decomposition of PCl5 into PCl3 and Cl2. So we can see that PCl5 reversibly gives PCl3 plus Cl2, and here the forward reaction having only one reactant PCl5 and the rate constant is Kf, and backward reaction there are two reactant PCl3 and Cl2 and rate constant is Kb. Now we are moving into the last type of the opposing reaction, that is the both the forward and backward reaction is of second order. Let us see the first example. A plus B reversibly gives C plus D. And here we can see that in the forward reaction we can see two reactant A and B, and the backward reaction also consisting of the two reactant C and D. So the forward reaction is represented by dx by dt is equal to Kf into concentration of A into concentration of the B. Here both the A and B are reacted in the same concentration, so it is represented as A minus X. Initially the concentration of A and B is A. After a time interval t, the concentration is reduced to A minus X. And the rate expression for the backward reaction is Kb into concentration of X whole square. So if we combining the forward and backward reaction, we will get dx by dt is equal to Kf into A minus X whole square minus Kb into X square. So this is the rate expression. So one of the example for this type of the opposing reaction is the gas phase reversible decomposition of Hi into hydrogen and iodide. So we can see that 2 mole of Hi reversibly gives H2 plus I2, and both the forward and backward reaction is a second order reaction. At the same time it is an opposing reaction. So today we will discuss the next important part, that is the complex or composite reaction. That means a reaction which is occur more than one step and the rate of a reaction depend upon more than one step. So this type of the reaction is very complicated. There are three different type of reactions are there: opposing, parallel and composite. Opposing reaction, parallel and consecutive reaction. So today we will discuss the opposing reaction. Opposing reaction is again divided into three different type depending upon the order of the forward and backward reaction, and we have already discussed the examples of the three different type of reaction. I hope you understood. Thank you.